Welcome to a deep dive into a performance bottleneck that often lurks in the shadows, even for highly optimized distributed systems. You've meticulously scaled your backend services, fine-tuned your databases, and optimized your API responses to perfection. Yet, your users are still reporting frustratingly slow initial page loads, leading to a suboptimal user experience. What's even more puzzling is that your core application metrics look healthy and network latency seems to be within acceptable bounds. Our monitoring dashboards, however, might reveal a strange anomaly: connection establishment times spiking to several seconds, often 5 seconds or more, during peak traffic. This perplexing scenario often points to an overlooked culprit: TLS handshake saturation, typically occurring at your load balancer. We're going to unravel why this happens and what senior engineers can do about it. Most engineers, when considering TLS, often perceive it merely as a minor network overhead, perhaps an additional 1 or 2 round trips, adding a negligible 50 to 100 milliseconds to the overall connection time. However, this perspective vastly underestimates the computational intensity involved in a full TLS handshake. When your load balancer receives a new HTTPS connection, it's not just passing data, it's embarking on a series of CPU-intensive cryptographic operations. We are talking about critical tasks like RSA signature verification, which confirms the server's identity, complex elliptic curve Diffie-Hellman ephemeral, or ECDHE, key exchange calculations for establishing a shared secret, and robust symmetric key derivation using a key derivation function. These operations, while crucial for security, consume significant processor cycles. On a quiet morning, an individual handshake might complete in a respectable 20 to 30 milliseconds. But during a sudden traffic surge, that identical handshake can balloon to an agonizing 5 seconds or even more, revealing a fundamental challenge in distributed systems. The core issue behind these dramatic latency spikes is queuing. Imagine your load balancer as a highly specialized dispatcher with a finite number of worker threads, each capable of handling a single TLS handshake operation at a time. These worker threads are the computational engines responsible for executing the CPU-intensive cryptographic tasks we just discussed. When incoming requests for new HTTPS connections arrive faster than these dedicated worker threads can process them, they don't simply get dropped. Instead, they are placed into a waiting line, or a queue. At this point, you're no longer just contending with the inherent cryptographic overhead of each handshake. You're also battling the additional and often significant wait time spent in that saturated queue. I have personally witnessed production load balancers at major technology companies plummet from an impressive 50 millisecond P99 handshake latency to a crippling 8 seconds during critical events, such as large-scale deployments or regional failovers, when thousands of connections simultaneously needed reestablishment, overwhelming the system's capacity. Here's where the problem truly spirals into a nightmare scenario. As TLS handshakes slow down dramatically, clients inevitably start timing out. Most standard HTTP clients are configured with a generous 30-second connection timeout, but mobile clients operating in less stable network environments often employ a much shorter 10-second timeout. When these timeouts occur, what is the default behavior? Retries. This means you're now contending with not only the backlog of original slow handshakes, but also a fresh wave of retry attempts, all vying for those precious saturated worker threads. This quickly pushes your load balancer's CPU utilization to 100%, creating a self-reinforcing negative feedback loop where every new connection attempt only exacerbates the problem. Furthermore, a deeper and often unexpected issue arises: session resumption, which is designed to accelerate subsequent connections by skipping expensive key exchanges, paradoxically stops working effectively under heavy load. When your session cache is under extreme memory pressure or your worker threads are completely saturated, even these fast resumed sessions find themselves stuck, queuing behind full handshakes, dramatically reducing the expected performance benefits. The biggest technology companies have encountered and meticulously engineered solutions for these challenges, offering invaluable insights. Consider Netflix, a titan of streaming that experiences massive, predictable traffic spikes, especially during new show releases. They've learned to maintain minimum connection pool sizes even during periods of low traffic, ensuring a baseline of established connections. More proactively, they utilize sophisticated predictive scaling mechanisms to pre-establish thousands of TLS connections 10 minutes before a major show release event. This strategy, known as connection pre-warming, ensures that when the anticipated traffic surge hits, a vast majority of client connections are already warm and established, significantly reducing the demand for new, expensive TLS handshakes. Cloudflare, at the forefront of internet security and performance, faces a different magnitude of challenge with constant malicious traffic. They deploy eBPF programs running directly in the kernel to filter out obviously malicious or malformed handshake attempts at line rate. This critical defense prevents these wasteful requests from ever reaching user space worker threads, thus safeguarding CPU cycles for legitimate traffic. Furthermore, Cloudflare employs highly efficient work stealing queues across hundreds of worker threads, preventing head-of-line blocking when one worker might encounter a particularly slow or problematic operation. The journey of large-scale infrastructure providers is often paved with hard-won lessons, and AWS provides a stark example concerning certificate rotation. In 2019, a routine certificate renewal inadvertently triggered a massive wave of full TLS handshakes across their entire application load balancer, or ALB, fleet simultaneously. This occurred because all previously cached session tickets became invalid at the exact same moment the new certificate was deployed. This sudden invalidation effectively negated the benefits of session resumption for a vast number of ongoing connections, forcing clients into full, computationally expensive handshakes. The incident highlighted a critical vulnerability in how large-scale certificate management can impact TLS handshake performance. Learning from this, AWS now meticulously staggers key rotation processes across different availability zones. Furthermore, they implement a strategy of gradually expiring old session tickets over a period of hours, rather than instantaneously invalidating them within seconds. This gradual transition ensures that the impact of certificate changes on session resumption hit rates is minimized, preventing a thundering herd problem where millions of clients suddenly need to perform full handshakes, thereby safeguarding the load balancers from overwhelming saturation. Translating these lessons into practical steps for your own environment begins with diligent monitoring. It's no longer sufficient to merely track the total connection count. You need granular visibility into handshake latency at critical percentiles, P50, P99, and crucially, P999. These metrics will illuminate latent problems long before they impact your users. Additionally, closely monitor worker thread CPU usage and queue depth on your load balancers. A high session resumption hit rate is also a strong indicator of a healthy system. Beyond monitoring, proactively implement connection pool pre-warming within your client applications. If you have predictable traffic spikes, perhaps during deployment events, major marketing campaigns, or the completion of large batch jobs, establish extra connections beforehand. A simple cron job or a scheduled task that opens, say, 100 idle connections and keeps them alive can significantly mitigate a sudden thundering herd of new handshake requests, safeguarding your load balancer from saturation. Furthermore, optimizing your worker thread count based on CPU cores is vital. A common misstep is configuring too many worker threads, which ironically leads to excessive context switching overhead. The optimal sweet spot for CPU-bound cryptographic work is generally around CPU count times 2. Employing SO reuse port at the kernel level is also a powerful technique to effectively distribute incoming connections across multiple worker processes, enhancing parallelism and efficiency. For systems operating at serious scale, additional advanced mitigation strategies become indispensable. One powerful technique is to deploy intelligent circuit breakers that actively detect spikes in TLS handshake latency. When these predefined thresholds are breached, the circuit breaker temporarily intervenes, rejecting new incoming connections with an explicit HTTP 503 service unavailable response. While this might seem counterintuitive, actively rejecting connections when your system is overloaded, it is a critical defensive maneuver. It's far better to gracefully reject new connections, allowing clients to retry with an appropriate backoff strategy, than to let the internal queue grow unbounded, which ultimately leads to system-wide paralysis and timeout cascades. By shedding excess load, you protect the health of your existing connections and provide a chance for recovery. Furthermore, for extreme performance requirements, investigating hardware offload solutions such as Intel QAT or AWS Nitro can provide significant benefits. These specialized hardware components are designed to accelerate cryptographic operations, dramatically reducing the CPU burden on your main processors. However, it's crucial to understand that even hardware offloaders have their own fixed queue depths. Without robust software-level admission control mechanisms in place, you risk simply relocating the bottleneck from CPU saturation to hardware queue overflow, a problem that is often even more challenging and opaque to debug than a software queue issue. A holistic approach is essential. In conclusion, while often overlooked, TLS handshake latency can evolve into a critical and hidden bottleneck, undermining even the most meticulously optimized distributed systems. It's a subtle but powerful force that can degrade user experience, trigger cascading failures, and introduce instability into your infrastructure. Understanding the underlying mechanics of cryptographic overhead, the perils of load balancer queue saturation, and the surprising failure modes of session resumption under stress is paramount for any senior engineer or architect. By implementing sophisticated monitoring, proactive client-side strategies like connection pre-warming, and robust server-side controls like circuit breakers, you can effectively mitigate these risks. We've covered theoretical concepts and real-world strategies from industry leaders, but sometimes seeing is believing. We've prepared a comprehensive, working demonstration package that allows you to observe this phenomenon in action. You can run it locally to witness TLS handshake latency degradation in real time, watch your dashboards turn from green to red, and see how intelligent mitigation strategies can prevent total collapse. I strongly encourage you to explore the provided GitHub repository. It includes everything you need: an Nginx load balancer with intentional limitations, a Go backend, a Python load generator, and a modern web dashboard. Run the demo, experiment with the traffic patterns, and gain invaluable first-hand experience with this critical performance challenge.